Sir, please continue.
So, good afternoon all. Share my slides. Uh, So, I hope my screen is visible to all of you.
Yes, sir.
Yes, sir.
Okay.
Please make it full
So,
screen.
okay. So, yeah, again, I welcome you all for this session on basically implementation of analog front-end hardware for high precision BMS application. So, let me tell you the very first background what we are going to discuss in this particular session. So we have a lot of things going on when we talk about a BMS system. It includes both hardware, it includes hardware to software interface, software side also, and software also at different levels, like very high level processing. There's a microcontroller level, very low end processing, which requires minimalistic algorithms, but very precise timing and much faster operation. So this particular session focuses on uh, one unit of the hardware, not the everything which is involved in BMS, because the time constraints and the details involved, I have constrained myself into this much part only. So let me first introduce in some slides that how uh, this particular unit is and what are the things related to this particular unit. Then we will go into the hardware implementation side as the title says, and then where I will go into little bit design intricacies. So let me start with the very first thing. So I will go through in a way that first I will introduce, I will talk about a little bit about the standards involved here. Then we will go to some of the features and how to take care of them when we go for an hardware implementation. Then we will be going on and standard IC design or a standard IC site, sorry, not the design of IC, but surrounding the IC. So whatever I am discussing here as an implementation, it is very generic and it can be actually used when it comes to the real-time implementation using a microcontroller. But there are some dedicated ICs which can be involved here and which can be used. So I'll be discussing one by one into those. And first I'll discuss as a generic scheme and generic approach. Then I'll be going to the next thing, which is the IC approach of it. So, I mean, as a general discussion, we know that ultimately BMS is basically taking care of the health of battery, but not only that, with that health, it also takes care of the charging, discharging, balancing. Many things are there. So if I want to keep those things in a particular category, so how would I keep it? Or in what category I will say that a BMS is working? So first thing which I will say is that it senses a lot of data and it optimizes the sensor data to utilize into the real-time estimations as well as some important actions. For example, there is a problem in the BMS, let's say somewhere there's a short circuit. So BMS has this responsibility to detect a particular short circuit or fault scenario and isolate the faulty section, as well as uh, let's say there is no big, let's say big short circuit or something, but there are small differences between the voltages when it is being charged. That also comes to BMS to take care of such situations. And over and above, it sends important information to the main processors to, let's say, have estimation of various parameters. So I will always say is uh, more like a guardian for a battery pack. Takes care of everything. And you can look at the number. The BMS is responsible for taking care of many cells. They are actually thousands of cells which we are talking about. They are packed in small, let's say, profile, and each cell is very tightly packed with each other. But to, I mean, schematically talk about it, it is nothing but many such cells packed together into, let's say, series or parallel combinations, and such modules are being replicated to form a pack. And a BMS has to take care of everything. Now, if we come to the general BMS thought, this is how people do. I mean, there will be a central processing unit which will be significantly powerful processor. We can think of it as a mini CPU, more like a DSP based system, which will take care of a lot of heavy calculations. But this unit, which we talk about, has sort of very dedicated task, which is more like brain. But it needs to have some smaller units which sits nearly at the battery, like exactly at the battery pack they sits, and then they monitor a lot of data there, and that data is being transferred to this centralized unit, and this is where the all processing happening. But today's topic, uh, which is more like AFE, for the battery pack management or BMS management, focuses on the basically these smaller parts which are responsible for near battery operations. So this is one of the most common architecture being used in BMS today in EVs. It's called as central one. And basically, if you look at a BMS pack in real time, you will realize that there are always some central controllers sitting there, and these controllers, which have usually a DSP installed in it, we'll be looking at many data together. But this data is not directly being sensed by this particular unit. Always there are additional cards, additional hardware sitting near to each battery pack, which takes care of this whole data. And it has all kinds of data. I mean, it has voltage, it has current, it has temperature. Not only that data, it also has a small memory to record a particular data, send the recorded data to somewhere, have a lot of communication with the interfaces. So we will look into if you talk about the BMS architecture, it has ultimately three layers. One is which is cell level, means you are looking at each and every battery pack, and within the battery pack you have various small cells together. And looking at each battery, taking care of the things at each battery level is the cell level. And generally, this is where the AFE, which we call as analog front end domain, it comes into the picture. And today's topic focuses over this particular part as a hardware implementation, means when we really try to implement it in our own product, let's say, in that manner. Now, it has responsibility to look at the voltage, current, temperature, as I told earlier. Not only that, it has to have a capability to communicate with the higher end processor. Not only that, on this particular aspects, other than measurement, it has to take care of certain stuff. One of those is protection, another those of is whether it is charging, discharging, and next thing is, let's say there is some problem, so it has to take care of those problems also. So we'll discuss into those more in detail, but what we will not be discussing is another layers, which are the layer 2, let's say. They have more high-end algorithms being, so those are more software oriented areas compared to the AFE domain. It is more hardware oriented, it is more whatever data has been collected by AFE goes to this next level, which actually samples data, uh, runs various algorithms over it, SOC, SOH algorithms, cell balancing, protection logic, system communication. And this is the layer which actually sends the information on an EV to the topmost layer. which is where you interact with the EV. So when you are running an EV, you look at the display and say, okay, this much battery is remaining and I can go this much far. All those estimations, all those data maintenance and communication with the driver or human interface is next layer. So this is third layer. So today we are not looking into third layer because it is more like embedded stuff. But full hardcore BMS, there are two things. One is layer 2, which is more like software algorithm, and layer 1, which is more like hardware algorithm. And this is where we are going to focus. Now, if you look at this particular side, which is AFE card or a unit, this is more like this particular unit, which is being shown over here. These are the small cards which I was talking about. They are called as analog front end unit. Sometimes some people also call them active front end unit, but usually the more common or more accepted terminology is analog front end unit. It has various responsibilities, including sensing, filtering, protection feature, relay features, and communication of the data, and some small data management as well. So we will go through most of the components over here, why they are sitting here, what they are doing, plus moreover, what and all we need if I want to make my own AFE card. So that's where we will be focusing. To do that, we have to look into its features. And looking from the feature, we will estimate what hardware would be required. That's how we will proceed. So if you come down to the block level of the same PCB card, what you will observe is that there is a one end which is actually the battery end, and there is another end which is the could be a big capacitor sitting here, and then there is a converter which feeds to your motor in an let's say um, EV environment, or otherwise it could be some other situation like there is a supply coming in and charger sitting there which communicates to the HV side. So basically it can be load also, it can be source also. So it can have a charging situation or it can have a discharging situation. Both are possible. Now, if you talk about general terminology, so we usually call that this is the battery side and this is the HV load side. And both of those have their own negative end. Uh, you would say that this is Earth or this is Earth. But in usual terminology, when we implement an AFE card or AFE hardware, generally only one side of this is Earth, and it is mostly the load side which is being Earth. And there are components coming in between. They result into a small voltage difference between these negative terminals. But we'll discuss more about that. The central part is more like a microcontroller. So whether it is a dedicated IC or it is a customized AFE card which we can make, that's what I am talking about today. There you will see that there is a central processing unit sitting. And that central processing unit is most likely a microcontroller, which is low-end microcontroller. It does not have very high capability, same as DSPs, but it can do lot of work at very high speed, more like an STM32 um, chip or so. Now, within this particular chip, there are various blocks. For example, there is a block which takes care of CAN bus communication. There is a smaller communication module which has a communication within this board. From some ADC, some other units, you can actually have various communication coming up and going on. Now, next thing is uh, uh, there are certain block of codes which are sitting to take care of. Uh, uh, is my screen visible now? Because I see that my screen is not. I mean, it came out of the sharing automatically. I
Yes, sir.
Uh, is my screen visible to all of you?
Yes, sir. Now it is visible.
Okay, okay. So actually in between it automatically went out of the sharing. That's why I was asking. Okay. So I hope whatever I was saying is relatable till now. Okay. So within this IC, I was saying that various blocks some blocks are dedicated to voltage sensing, some are dedicated to fault condition sensing and taking various actions. But other than this central microcontroller unit, if you come out of it, there are various things. Like one of those is there will be a fuse sitting. Near to that fuse, there will be another switch sitting. Generally, these are solid state relays. And there are some other pre-charge contactors. Pre-charge means when actually no load is being, let's say, being fired, there is a capacitor generally sitting over here we need to charge that capacitor that particular. So we have some pre-charge circuit to just charge it out. Once it is charged, then we can actually have a energy transfer between a battery to load side or even charge it through some supply. Generally, always some sort of insulation resistance added, additionally resistance added to chassis ground to the actual unit. So this is just the block of it, whatever card I was telling you about. If you go into the details of features, you will get to know what these blocks are doing one by one. So before I go into the, let's say, the feature part, the first thing is standards. So there are various standards which talks about the BMS AFE design. So basic thing is that there are various international standards and we have to adhere to those because if you are making a product or something, let's say some card, it has to follow through several standards. Now, if you try to sum them up, what do they mean? Actually, they are all talking about several protections, several let's say precautions to be taken care. And if you take care of, let's say, over voltage, under voltage, over current, let's say over thermal conditions where temperature is being raised, or some sort of overload is there which is sustained for long time, all those situations you need to be you would be able to sense if you take care of all these standards even. So basically these are guidelines to help you out, in fact. Like ISO 26262 automotive says about functional safety. And similarly, you can look that there will be some will be talking about the cell level safety, some will be talking about the immunity wise, some will be talking about the fast transitions between various states and all, some would be communication oriented. So I will be giving you some markers when we are discussing one by one these features, that what you can set or what you can take as parameter which will fall within this standard. So you can go into the details of these standards and try to make out more parameters what I am discussing over here. Because these are more generic standards and they have more domains to be covered, not only about AFE, they are actually focused on various parameters, including AFE cards. Now, if you talk about the basic feature first, which is voltage sensing, so what you will observe is that within the battery bank, there are various cells involved, and through each cell, there will be some sample coming up. So, if I talk about, let's say, 7,000 cells are there, you will observe that at least for voltage, 7,000 datas will come, but they will not come as together into one unit. One unit will be taking care of, let's say, 48 cells, or maybe little bit more, depends on the configuration. General configuration is more like 12p 16s, means 12 12 strings are in parallel and 16 are connected in series. So you can just multiply 12 by 16 and you will get to know how many such cells are there. So all of these cells have to be connected to some sort of cell balancing circuit, and that data should be transferred to the AFE core, which is the main brain of the AFE. Why is it important? Because various features, especially like state of charge, which on the which basis you say that how much battery is charged, how much it is discharged, all those features depends on the actual value of the voltage and monitoring of the current. So basically voltage and current has to be sensed at each level. Not only that, some protections have to be monitored through voltage. Um, and then there is a higher level algorithms running. With these algorithms will take care of the state of health, which will actually make your battery run longer in lifespans. So, like health monitoring. So basically, there are multi-purpose utilization of voltage data, and this data may vary from instantaneous decisions to the long decisions. Uh, Even some decisions which are taken care at the repairing and maintenance level. When you go your service routine into the let's say fifth service or sixth service of your car, then what happens that they will look at this data. Based on that data, they would know ki which components are actually tracking things very well, or which components need to have a repairing and all. So this also is a very helpful data when it comes to that. So some data, some samples have to be recorded there in the master data storage. Now, if you just look at the, let's say, voltage sampling or voltage sensing, how problematic it is when we come to real life scenario. So, one thing we need to understand that it is very critical, very prone to error. And you can think like it that there could be various cells. One cell may be at 3.8 volt, another can be at 3.9 volts or something like that. But think about it, the lowermost cell is at near ground like this one, and the uppermost cell is near the high voltage side. So basically you have various situations like one cell which is sitting at 48 volt and it has 3.8 volt, another cell which is sitting near ground and it has 3.8 volt. Sensing these two at the same time and without error is actually challenging. For example, you have 12s lithium ion pack. It means 12 batteries are in series. Now, in series 12 batteries, you know, first cell is 0 to 3.8 volt, and last cell is 41.8 to 45.6. And if you try to find out a common mode voltage, means the average of the voltage between these two ends, you will have various voltages. So there is a lot of common mode voltage which we need to bear, which we need to look at. Like if you think about it, your microcontroller is running at 3.3 volt or 5 volt. Now you are sensing something which is sitting at 42 volt and it has some particular voltage has to be sensed and sent to the microcontroller. So it becomes very complicated job for us when we do it. And errors are also very, very dangerous thing here. So how do we do it? Generally, one of the technique is we use something called as resistive divider and differential amplifier. It is most basic and most easy to go to sort of sensing. So what we do is that we have some voltage being sensed, which is more like battery voltage, and then voltage divider. Through that divider, we generally it is op-amp based because differential means we are sending a data which has nearly same voltage. It helps us to cancel out some sort of noise or some sort of signals which are present in both the terminals, and it actually helps us to amplify the data. Now, major thing about it is that if you implement such circuits, na, there is a lot going on which we do not take care when we really do. So, first thing, It's like, let's say you used a resistor which is 0.1% tolerance. Means if you just put those resistors which are normal resistors like 1% tolerance and 0.1% tolerance, there's a big difference at the site. Like for example, 1% mismatch at 1 kilo ohm divider cause 10 millivolt error at 4 volt, which is unacceptable. So we need to go for very high precision resistors at the sensing end. That's what I'm trying to say. So normal resistors can't be used. When you are actually making your own sensing scheme, you need to look for resistors which are very high precision resistors. Then next thing is you need to take care that this particular voltage division is not being affected by the next connection. For example, there's a current flowing through this particular path and there's another current flowing through this particular path. It actually causes your voltage balance to get sort of in a zone where you did not plan for it, because the whole study of voltage divider is based on what, that this current flows through serial, like there is no current going in this path. Impedance matching is very important. So input impedance at this particular site should be infinite and it should not take any current basically. So those are some basic precautions we already do when we are implementing an amplifier sort of circuit. Same is true over here. But another approach is also there. I mean, you use your resistors and op amps, it causes one problem. That is, you are actually taking a lot of energy through it, and through that energy, you are going to sample the data. So it results into some extra losses. That's what I'm trying to say. Now, if you want to avoid those losses and you want to keep it minimalistic, there is other approach which is called as flying capacitor. Reduces our problem of, let's say, common mode noise and all. So what we do is we take a capacitor, wherever we want to measure, we connect this capacitor, let it charge a little bit, and then we measure that data. Through that, we know that, okay, this particular battery is charged at this voltage. So basically, this capacitor will be connected to this battery, and then we'll get to know the voltage of this battery. Then again, this capacitor will again connect into the next battery and get to know information about the next battery. And so on, we can keep on repeating. So, in fact, in this whole thing, we use certain switches, some switches which can connect this capacitor to a particular battery, let it settle for some time, and then again use it to the next one after reading. So, just for an example, at the design level, if you are such circuit, generally there will be a switch resistance. When you turn it on and current flows in, there will be some resistance involved. If you take consideration of that resistance and the capacitor you have used, there will be some time constant appearing. RC, we know that as an electrical engineer, we have already known that with capacitive circuit, the time constant is RC, and nearly 5 time constant, 4 time constant we want to stay before it is being charged fully. So when you are connecting it to a battery, you want to be sure that the energy has been transferred and it is being charged. So for that, you stay for, let's say, 5 tau samples, and it gives you a really good idea about how much time it will take before I can really read it. Even before reading, it has to get to charge to the voltage which we want to read. So if you do these calculations, let's say 25 microsecond settling time I want. So I can, look for 5 tau, and through that I can actually calculate resistance and capacitance. That's what I am trying to say here. So you need to sort of take care of various parameters here. Now, one of those parameters is certainly the energy being transferred should not get lost. So lot of resistance is not good. A small resistance should be there, should not be in kilo ohm zone. Second thing is should not take a very large time to do that. Should be a slow transition of the energy. Plus, as well as it should be not too slow. For example, what do I mean by slow? I mean to say that it should not be like megahertz sort of fast, because when things go that fast, now a lot of noise comes into picture. I don't want that noise to come into picture. I really want to avoid all the unnecessary high frequency noise there. So to do that, we actually put a sort of RC element which falls into these two bands. One is it can sample fast enough for my data to be transferred, and another is it should not act very fast, like in megahertz sort of range, to avoid all the unnecessary noise systems. First, these things, and second things which we need to take care is, which I have not written over here, is that generally these wires and the leads which we are connecting there have some inductance involved, which causes our circuit to become actually RLC circuit, which has a damping nature like this. And this damping nature should be avoided at all costs, because it can overshoot into some values which are not safe for your battery itself. So we have to take care of these certain parameters when we are, let's say, designing. General considerations are keep it something like 25 microsecond, 20 microsecond, and it is coming from some of the standards, the number which I am giving here. Now, same thing, when you are actually reading this data, one thing is that when you are reading, you should not create a noise. But reality is there is a lot of noise already. So you are running your system into an EV. There's a lot of high power equipment around it within the EV itself, which is high power inverters and all. So they create a lot of noise there, lot of harmonics, and that is being radiated into the system. So when you read it, you actually capture a lot of noise there, and this noise could be in like something like 20 to 200 kilohertz for switching converters. Then there are other PWM signals are also involved within that drive, uh, uh, which may cause some other sort of noise. Then there are radio frequency communications being around the EV within EV itself. So if you talk about today's EVs, we are talking about connected vehicle, which are communicating through 4G or 5G to each other. Uh, like two EVs are going on and they know that they are going on. There's always some communication happening. So this communication causes a lot of noise for us when we want to sense it. So we need proper filtering and all when we are actually looking at the data. That's the take home message, that lot of noise is already there. You take care that you do not introduce extra noise, but it is there. So you need to filter it out, whatever it is. The signal which we want to look at is going to be a continuous signal, but we have limitation over the systems which we are running, which are sampled system. So we may have a low frequency sampling, which actually causes us to have a near approximate signal compared to a continuous, or we can have a very high sampling rate for the frequency. It actually tracks back to a continuous signal or actual data which we want to monitor. So we need to have sufficient high frequency. We cannot be having very low frequency. Like suppose I am reading a data at 10 hertz. It means once in a 10 times in a second, which is looking at a battery is good enough actually, because we think, okay, it takes hours and hours to charge. So in a second, if I look at it in 10 times, that should be enough. But the real fact is when there are mismatches, there are problems, there are faults. That time things go much faster than what it takes to charge a battery or discharge a battery. So we need to have significantly higher sampling. Truth is, we can have ADCs running at something like 1 mega samples per second. And actually, this 10 hertz or 20 hertz update is not being taken in practical scenarios. Practical scenarios, you need to have much faster sampling, something like kilohertz of the frequency. So generally, this is the scheme. So we would have sampling somewhere at 1 kilohertz. For example, we are reading the signals at 1 kilohertz. And then we need to introduce a filter uh, after that data which we have read, which will filter out all the switching noises, all the radio frequencies and all. To do that, what we do is at little bit higher frequency, we keep our cutoff frequency of a filter, and actually the gain of the filter goes low for high frequencies. For what does it mean is that ultimately you are giving one gain, no amplification, no deterioration of the signal, whatever you want to read, like 1 kilohertz signal of the voltage data. But if there is a switching frequency component at let's say 100 kilohertz or so, you are actually trying to attenuate that component to a very small value, or let's say over here. So what does it mean? Mathematically speaking, minus 40 dB. Minus 40 dB means like you are making the signal 1 by 100 times smaller. Like suppose there is a noise which is coming for 0.5 volt. You divide that 0.5 volt by 100. That much will be transferred if it is minus 40 dB. So you are actually making the noise 100 times smaller. Good part is already over the main signal, the noise would be a small number. So if you make it 100 times smaller, it nearly goes away. So that's the logic. And then next thing is that usually you do not like filters which, I know all of you might have known that second order system has a peak over here, something like that. So that sort of peaky nature we do not want, because it actually amplifies a particular band of frequency. In filters, we do not carry it out. We do not want it. So how do you design a filter? Basically, it could be as simple as a low pass RC filter. So you put some resistive IC, some capacitive IC, and you expect that there will be an input signal which will get filtered at the output. And design principle is very simple. Like you take 1 by 2 pi RC as the cutoff frequency or the filter frequency, and then you you pick some resistance value which is in tens of kilo ohms, because you do not want a lot of current flowing over here. So suppose you are dealing with a 4 volt battery cell. 4 volt divided by 10 kilo ohm will give you a very small current, and that is workable for us to take that much current. And then there is this capacitor which gets charged, and in a way that it filters all the noise, but it retains the main function or the main signal being come. So you can simply do, if it is 10 kilo ohm, this calculation, it comes out to be 15.9 kilohertz as the cutoff frequency. As I was telling earlier that it should be even lower. It should be something like 5 kilohertz, 4 kilohertz. Those numbers are more practical. But what does it mean if suppose I have 15.9 kilohertz as the cutoff? It means that if I make it 10 times, which is like 159 kilohertz, I will have a minus 20 dB attenuation. Minus 20 dB attenuation means whatever signal I am giving, that signal becomes one tenth of the value. So more like um, something like this, that if you have some signal V input, when it gets transferred over here, it becomes V input divided by 10 for 159 kilohertz frequency. So it's not always. If you have a 1 kilohertz frequency signal, whatever it is transferred into same magnitude. So the point is that any signal coming at proper frequency transferred as it is, and any signal coming at much higher frequency will get small, small and small and small, so that you attenuate all the noise. That's the purpose. But truth is, frankly speaking, in an EV system, this filter is not doing good. Making noise 1/10 doesn't work out very well for EV systems. When we are looking at the EV systems, we need to have more filtering. So this is one of the fundamental simulation with some data over there, and with that data, you can see that there is a lot of noise involved, EMI noise with this data. And when you connect it to filter, actually your data comes out to be pretty flattened. But actually there is some fluttering is still present. That fluttering itself is not allowed. It is a small number it from our eyes, but when it comes to a BMS or AFE system, it is not good. So we try to remove that also. And to do that, we usually do what? We do come at something called as second order filter. It has capability to give minus 40 dB decade, means whatever cutoff I take. Like for example, I have taken cutoff of this particular number, which is uh, 10 kilohertz. It means that 100 kilohertz signal will get V input divided by 100, means 1 by 100 times it will actually drop down the signal. So a noise which becomes 100 times smaller, that's what I want. And to do that, I would like to have a second order filter. And there are many second order filters, by the way. This is just one circuit which I'm showing here. And they are all following standards, so there is no problem. But one thing we need to take care is what? That you need to take care of the quality factor. So basically, any filter you are designing in BMS or for AFE, it should not have a lesser quality factor than this. Because if you go lower quality factors, uh, uh, it becomes very sluggish. If you go much higher quality factor, it becomes another problem, like things becomes underdamped or so, more gains come into picture. So point is that these quality factors should not be high to avoid unnecessary amplification of some frequencies, and should be not very low to avoid very slow operation of the filter. So I need to have a filter which works really well, responsive, but at the same time, it should not have unnecessary damping. So what I am trying to say here is that there are two possibility of a signal. Like for example, your voltage rises like this, but this is what it should be reading. But if you do not design it properly, what can happen is that it becomes a very sluggish system and rises very slow, or it could be very fast system and it goes something like this. So these two behaviors I don't want. So I really don't want to have a small quality factor which makes my system very slow to response for filter. I don't want to have very high quality because it causes lot of let's say oscillatory behaviors. That also is very bad for my systems because I'm actually ultimately trying to do some sort of filtering, and with that filtering I want to have several and operating parameters coming up. So those things I'm taking care over here. The next thing is let's say if we are making such let's say filters, what are the parameters I need to take care? Like one of those is I need to have an op amp which has rail-to-rail essential feature. Rail-to-rail usually if you give 0 to 5 volt, it has capability to work nearly from 0 to 5 volt. A little like 100 millivolt or so offset should be there. But generally, we can think like that, that from 0 volt to 5 volt, it can work. It does not have a necessity to give me at least 1 volt at the input, then only I start working. Or at most at 4 volt I can work. If you go more than that, I cannot work. This type of situation is generally present in all op amps which are not rail to rail. So rail to rail op amp is a terminology which we want to have in our op amp. Another thing is I need to have a high bandwidth, again bandwidth product to avoid unnecessary noises, but at the same time give significant gain to my utilizing frequencies. And these things are general things like low offset voltage, low bias current, expected for all ICs, not only for op-amp. Some devices which are suitable to such standards I have mentioned. So if one of you, let's say, design your own card, you can have these ICs for the op-amps for the filter. These are good enough to go with. Next is that you need to take care of that filter related parameters. So basically, you should not have capacitors or resistors there which will have a lot of tolerance, like 5%, 10%. It causes your frequency to deviate, which is your cutoff frequency. You may be thinking something ki, okay, at 100 kilohertz it will do something like 1 by 100th of the thing, but it will not do if it is not a properly designed system or proper components are not placed. So you need to have very tolerances for your component, as well as they should not have much variation with temperature, because all of you know that our country needs a lot of variation of the temperature. If you just go by a ride, if you are sitting in Delhi and if you try to go to Jaipur, a lot of temperature has increased, and then if you try to go from Delhi to Uttarakhand, the temperature falls. So there is a lot of variation in the temperature. I don't want to have components which will vary with temperature. So as far as the temperature, as far as the voltage and their operating conditions are concerned, the component value should not change. That's what I'm trying to say. And for resistors, generally it is 0.1%, which is fine to go with. For capacitors, less sort of precision rating is fine to go. Now, next is that's what the reality is. Like there is a battery pack, lot of signals are coming in, there is a cell balancing circuit, and then there are RC circuits which are sitting for each, let's say, signal to go forward. So basically, it's being filtered. That's what I'm trying to say, and it is always there. So if you look at this card, you see a lot of connectors here. So these connectors are basically to put in the conductors. Now from these conductors, you see a lot of RC components are here. Like if you look at here, in this portion, you can see that there are SMD resistors and capacitors are sitting, and a lot of them. Why? Because you know that there are many cells which we are uh, mm, sort of you want to look at many such voltage and related data. So with that data, you want to filter it out with uh, RC or second order filters sitting near to your input, and it is very common practice to have them. So you will see that whenever you look at an AFE card, the first layer is this RC components. Next is with these filter designs, next thing is like you want to sample the data, and you want to read it out. So to read it, actually what you will prefer is something called as uh, multiplexers. So when you are using multiplexers, what you do is that you actually have something called as single ADC sampling into various inputs. Why is it needed? Because I cannot put an ADC to read each and let's say coming data, because it causes a lot of problem for my cost plus size parameter. Each IC requires its own bias, its own filtering circuits, its own reading circuits and all. So we do not like to do that. We try to put one IC and it should have capability to read many samples. So what we do is that usually we multiplex the data. So this is called as multiplexing of the data, where one ADC is reading to many cell data. Generally, we go for 8 input ICs which are there, and there are some 12 input ICs are there, but they causes slow sampling of the data. So you need to understand that if I want to read 8 data from one ADC and it is running at 1 megahertz, megahertz goes to many cycles for just for one data, something like 20-25 cycles. Then again, if I read 8 data out of it, so 25 multiplied by 8. So 200 cycles are required just to read once this 8 data. So we do not like to do many input through one ADC, like 12 or 20 or 50 or 100, but 8 is a decent number. That's what is being used in the industry. So they would put ADCs which are sampling something from 10 to 12. That's what usually the order at present is. I mean, ADCs will become faster with time, and we will be able to sample more and more data through one ADC. But at present, the standard is 10 to 12. Now, when we do that, this multiplexing, there are many noise which are coming from, let's say, the filter side. So, what I was telling you for the filter or the data, it's also applicable to input side of ADC, because ADC's input is that filtered data. So, various precautions are there which goes into ADC side also. Like one of those is it should not take lot of current as input. Again, same thing which I told you is true for many ICs, that we want to read the signal, we don't want to take the current out of it. And the second thing is it should have a really good switching transients. I mean, you can see that I am moving between various signals. When I move to various signals, it should not have some sort of noise or overdamped, underdamped sort of behavior. It should have a really good, quick, and sort of very good damping situation. Same as I would say critically damped also. So something like that. As well as there should be a fast sampling time coming up from the ADC. Uh, like I want to read a lot of data. Uh, I don't want to wait into the situation that I am waiting on the data to come. It should not become too slow. That's what I'm trying to say. One more thing is that usually when you treat data through an ADC, you multiplex various data through single wire or single connection, and there is another situation where you actually read the data from let's say two wires or two connections. So there is a difference in between two. One is called as simple sampling or single-ended. Another is called as differential multiplexing. So what happens is that in the first case, the ground is fixed and the signal is being taken from various cells. Less possibility of catching some other noise which are available in the environment, like a communication noise. But when we go differential multiplexing, means we use two terminals to read any data. Uh, then what happens that you are reading at a terminal through the data, where one end is connected to the filter output, another end is also connected to filter output. So whatever noise is coming in, it will come in both of these. And when you actually try to read it, they get cancelled. So you can see that in the down one, if you use just the simple sampling, generally you will sense more and more common mode noise. While if you sense a differential cell voltage, it will have a very simple, let's say, effect that you are reading nearly same voltage all the time. You are not going into common mode zone like low voltage to higher. Always the difference remains nearly the same, as well as you cancel out many differential common mode noises also which we are being catch. So general scheme within AFE card is to go for a differential ADC sensing. That's what I'm trying to say. And most of the ADCs nowadays, they come with this differential multiplexing, so it's not a very big issue. Now, next thing without, I mean, going to the next section just about the ADC would be a little bit on the embedded side rather than just noise filtering. So if you try to understand the perspective that we are trying to do, that we are taking one ADC, trying to read much data from it. So let's say, for example, a switch has its own transient time, 10 to 100 nanosecond it takes to move from one position. Second is that when you read it, you take some time, like there is a resistance in the filter, there is a resistance in the switch itself which is connecting it. And then there is internal capacitor of filter. Then there is another capacitor sitting inside ADC, which is very small generally. So we can think approximately whatever resistance of the filter plus switch resistance is there. If you make a product with capacitor, you will see that there is a transition time. in sending the data from the ADC interface to the capacitor. That time, for example, in this case, whatever taken is 100 microsecond, which is very realistic number. It's not something which I am just telling you as an example. This is coming from the standards. Usually, if you use a standard proper switch in multiplexing, it will have 100 ohm sort of value. Filter, as I told you earlier, that we will take something like 10 kilo ohm and 10 nanofarad capacitor coming from the filter design. So you will have a number which is like 100 microsecond. Now you have your own 12-bit sort of some conversion algorithm for the ADC. So it also takes its own sampling time to conversion time. That is something like 5 to 10 microsecond for most of the ICs which we are using generally, and it takes its own small acquisition time, like just to read the data and then convert. So two things are there, it takes some time. So you can approximately take like 10 microsecond it is taking. And if you are trying to read various data, let's say five data or so, so with five data, we'll go to something like 500 microsecond, more than seconds. So I have taken typically 600 microsecond per channel. Now, if you take this much time to read, uh, and if you are scanning through 16 such cells uh, data wise, so it takes a lot of time for you to go through. And let's say 9.6 millisecond per full scan, like uh, throughout 12, 16 cells you are reading data, and just to look through it within your ADC to microcontroller, it takes some time, which is 10 millisecond per se, which is fine, which is good enough for a BMS. So here, when we are talking about BMS, this much time, like 10 millisecond, 12 millisecond, 12.5 millisecond is fine. Most of the manufacturers like TI, Infineon, they are using something like 10 to 2 in this sensing part. And if you look at this sequence of the strategy, usually you go from initial number of cell to the final number of cell, means each cell you want to read, and there is this mux selection happen, then there is a delay given by us, let the thing settle, then there is conversion that should be start, and once we get that conversion signal that okay, the conversion has happened, then we read it and we store it somewhere within the data transfer unit. So there will be buffer registers within our system. So those are all coming with, let's say, the next interface, which is from the ADC to microcontroller. So usually this ADC is being uh, communicated or being is talking with micro, and this data is being sampled one by one. So this is fine enough. We have lot of registers, lot of memory there to store the data and look at things. So basically, voltage sensing has these many basic things. Like first is the, just to look at the voltage, we need to have several arrangements. I would say, let's say you have some sort of R pot divider, then you have your own differential op amp. And then next thing is you need to have a filter. Then next thing is after filter you have multiplexing ADC. There also you need to have lot of data coming in. And then next thing would be coming up from this voltage sensing is cell balancing. So there are various reasons why we are doing this cell voltage measurement. One of those reason is that we want to monitor the voltage of each cell and make that to equal. So for example, you have various cells available with you. If suppose what happens that during charging, one of the cell is getting charged fast or discharged fast, then it limits the charging of the whole pack. So basically what happens that, let's say you are discharging and one of the cell is getting discharged, then it means that there and it also means that you cannot take remaining energy from the cells. So that is a problem when cells are not working at equal voltage. You can see that some cells have more voltage than the other ones. And that is a problem. We don't want to have such scenarios within our cells. So what do we want to have? That we want to have all the time equal voltage at each cell so that their charging condition remains same, and it helps me to sort of take most of the power out of the battery pack, or it helps me to charge most of the power into the battery pack. So basically it prevents overcharging and over discharging. That actually says that if you take more energy now, then this cell which is being emptied will get deteriorate very fast. Its age will deteriorate. सबसे problematic thing is that it will fail after some time, and I really don't want to have that. Next thing is it also enhances reliability and safety. For example, suppose your let's say this particular cell condition comes into picture in a way that it goes into overcharging condition. Then it will cause heating. That heating will be very bad for my system and things sitting around it. So those things we avoid basically. Now next thing is what we can have something called as balancing. So in cell balancing, what we do is that we have certain resistors connected to each cell, which are more like your RC filters. What you do is that whenever you need to discharge a particular cell which is being charged over, or you want to bypass some energy, you can create a parallel path for current. Like there is a switch sitting, it will turn on and it will cause the current which is actually discharging the battery which is being charged faster than others, and let the current flow through the battery pack so that every other cell is coming at the same level. So passive cell balancing is basically sort of power into resistor, and through that we actually maintain a constant voltage, or sorry, same voltage throughout the battery cell pack. It has various problems also, but it is very simple to implement. So it has one problem which you are losing the energy, so it gets heated up also, but major problem is that you are reducing the efficiency. Another thing is that it has limited capacity of current. Usually this discharging and bypassing requires a small current to go through there, because it is always sitting near the rest of the AFE system, and we don't want heavy current to flow there. So we take a very small current, something like uh, 200 milliampere, 150 milliampere is a common number which follows the standards also in general, which is very common for low cost EV systems, and it is very simple to implement as I told you. But if you go to little bit more sophisticated system, you have need of faster system, more effective system without unnecessary energy loss. Then you go to something called as active cell balancing. But if suppose you want to design such system which is passive cell balancing, so how would you design? So first of all, you need to recognize how much resistance you want to connect there. So you have some cell voltage, which you have good idea that approximately it is about 3.7, 3.6, 4 volt or so. And then you have balance current also available with you, which is 100 to 200 milliamps, as I told. It is approximately 200 milliamps for now in this particular example. And if all values together, it comes out to be 18.5 ohm in this case. And suppose I take a 18 ohm case and put this current flow through there. So what I realize is that it is actually dissipating something like 0.72 watt, which means I need to use an 18 ohm resistor, but it should have a capability to burn 1 watt of power, something like that. And if I take this much power loss through 1 ounce of copper, which is usual thickness of the copper track which we take when we are designing a PCB, what we realize is that it has a little bit temperature rise, and it is fine, it is workable, acceptable zone also. But when we are touching through the temperature difference, the ambience, which is 27 degrees Celsius in general, then we should not go with that much thickness of the copper. We should give more copper to the thickness, which is 2 ounce copper. It means the thicker copper uh, layers available within the PCB, which can cool faster. And because it can cool faster, it actually keeps your temperature little lower. So it is not a common resistor. That's what I'm trying to say. It requires more power to be dissipated, better temperatures to be maintained. That's how it is designed. And that's how it is chosen. That's what I'm trying to say. Now there is a switching element, which is this MOSFET sitting here. If it is a dedicated AFE IC, it may have within the IC itself these switches. But when we are making our own system, we need to connect some MOSFETs there. So generally we connect N-channel MOSFETs, which are generally low side driving, something like this 02 IC and BSS138. These are commonly used in BMS. So they have low logic level requirement, and one good thing about them is they can be directly fired through microcontroller. So if you look at the MOSFET analogy, it needs to have a driver, gate driver. But these MOSFETs are low power, low current, so they can be directly fired through microcontroller like STM32 GPIO. They require like 8 milliamps of the current, and STM32 pin are capable of giving 20 milliamps. So something like one IC is not needed additionally, which is generally needed for a MOSFET. But in BMS, the practice is during cell balancing, we do not like to have a MOSFET which requires a dedicated driver IC. And then around that particular thing, we can have some study of how takes to do the job. For example, if we take this particular MOSFET as an example, it requires particular charge to turn on, which comes from the data sheet. Like for example, 1 nanocoulomb in this particular IC is required. And if you take like 8 milliamps current, 1 nanocoulomb charge, then you see that 125 nanoseconds it will take. 125 nanoseconds it will take to just get the switch to turn on. Like the switch has turned on within 125 nanosecond. Like next 20-25 microsecond, the energy transition will take place and there will be a cell balancing happening, the way I was telling you earlier. So basically, these components when we select have to fit in the scheme well. That's what I'm trying to sell. And it requires all of the components to be considered. Should be the value, what should be the heating. Based on that heating, I need to design my PCB. Based on that, I need to select a MOSFET. And also I want to select a MOSFET which does not require a dedicated driver IC, which gives me a lot of headroom to design and to implement. And the next thing, I would like to look at an IC, look at an arrangement which actually turns out pretty quickly, and it gives me a lot of time to do my actual function which I want, which is cell balancing over here. But suppose I don't want to do a passive cell balancing, I want to do an active cell balancing, then I would be going through some other process. What I will do is that I will have something called as flying capacitor or inductors, which I would use to take any excess energy from one and charge into other battery. It actually gives me a capability to do this cell balancing, but without losing energy. For example, I have a flying capacitor. I connect to one of the battery, which I have observed that it is going higher voltage. So I will take some excess charge out of it, and then I will store this charge to the other battery. That's what I will do to balance the voltages. So it will increase the other battery's voltage. It will take extra charge from one of the battery and will give me a condition where I can actually do an effective active cell balancing. So now suppose I have a capacitor which I need to connect between two cells. So I need to have several switches, actually four switches to connect it to upper side or lower side, as well as give me capability to make the current flow any side. Like for example, I may need to take current from this side, or I may need to take current from this side, or I may need to take a bypass current, which is like I don't want to charge a particular battery. I want to take the current and then store the rest of the charge to battery. Moreover, such circuit would be needed near each adjacent battery. Like for example, one such circuit with one capacitor and full bridge is sitting at the top battery and second battery. The another would be sitting between second battery and third battery. Next will be sitting in the third and fourth battery, something like that. So each individual two battery pair requires a dedicated flying capacitor. So generally what we do is we do not put one bypass capacitor to each cell. We put pair by pair. Like suppose these two batteries will have one bypass active capacitor, this pair will have another bypass capacitor. Uh, and there will be no bypass between this second battery and third battery, because I don't want to put a lot of hardware there. That's what I'm trying to say. But it has improved efficiency. It has little bit higher cost definitely, but it performs really well. So this type of active cell balancing is preferred in the system where high density packing is there, like EVs. So you are putting your system within the chassis, over and above people are sitting over it. It is already in very heated environment. The EV is running, it is at high temperature. You would not like to add more heat to that. So that's why you would go for an active cell balancing most of the time. And all sophisticated EV systems, if you go a little bit higher in price, you will see that they all use active cell balancing. Something like two-wheeler or three-wheeler zone will go for passive cell generally. Now, how do we do that? Uh, it's still some design considerations are needed, even though you select a proper capacitor, proper switch also. For example, you select a capacitor which charges significantly quickly. Even after that, you are working with a full bridge circuit, which is inverter circuit, and we cannot actually turn on two switches within one inverter leg together. So what we need to do is we run one of the pair of the switch, which actually connects your capacitor to charge. Then we have to wait for some time before we turn on the other two. Like we will first close these two and then we'll sit there. That sitting time is called as dead time or dead band. Generally, dead band or dead time is provided like 100 nanosecond, 200 nanosecond or so, to let it realize the switches which were supposed to turn off are actually turned off. Then only we turn on the other switches. Usually, if you just do quickly, what happens that even though you do not have any signal connected to S1, it is on and the other one is also turned on. So it actually has a short circuit across the battery, which causes a lot of risk within the system. Again, overheating, and there is even chances of fire within the battery. So we will have to wait. So generally what we do is that we turn on this S1, S4, then we let our capacitor to charge something like 1 microsecond, we wait, and then we give a dead band, which is every one of these switches turned off, none of them is on for 100 nanosecond. Then we connect our C-fly or this capacitor to discharge path. Again for 1 microsecond we let it discharge and then again dead band. So there is waiting for charging dead band, discharging dead band, something like that. So our microcontroller signals which are taking care of this active cell balancing should come in that sequence. That's what I'm trying to say here. Now, next is, before going to the next part, let me tell you that this is all we do just for voltage monitoring and voltage correction basically. So we are taking care of the measurement and then we are taking care of the voltages. We are assuring that they are equal or they are into the zone. Now, next thing is that there will be some solid state relays sitting there. Means whenever you try to charge your battery, there will be one path of the current which could flow and charge your battery. There will be another chance which is like discharge of the battery. Both are taken MCU or the unit sitting at the AFE card. So if you want to charge, one of the switch will turn on, which is charge FET in this example, another diode will be running. And if you want to discharge it, the other switch will get turned on and the battery energy will go here to here. So basically, thing is when you are running an EV and you want to transfer the power to motor, there should be discharge F which should be turned on. And if you want to take the energy and charge your battery cell, there will be a charge MOSFET which gets turned on. And both are open when we do not want to get a connection. In any circumstances, we usually do not turn on both of them together. That's what the philosophy is. But truth is, when we turn on any charge effect, we do have tendency to turn on both. Not actually like any diode to transfer the energy. For example, there is a discharge fed turn on situation. So this energy goes from this diode, this FAT, but if it is also turned on, the energy do not go through diode. So truth is, once we recognize that it is charging condition or discharging condition, we turn on both FETs and we do not want any other overheating scenario due to diode also. But the thing is, first we need to recognize which to turn on first. After some time, the second one is turned on just to help it out, help the situation out. So this is something like this. So big switches will be sitting there, high current capacity, 100 amps, 200 amps, something like that. And they will take the charge of the charging and discharging. They also act as solid relays. Whenever there is a problem, they will turn off both of them together. So no path is being formed to transfer the current. So more like they provide overprotection, over current protection if you turn off them properly. Means overcurrent is not there inherently, but they help whenever we want to stop an overcurrent to switch off the circuitry. And many things are there. Like due to time constraint, I would not go through each of these point. But if you have an AFE card, let's say market purchase you take, what you can see is that near the sensing part, a lot of filters are there, as I told earlier. Then there are big switches sitting, you see, and there is a danger sign inside. So this is what they are saying, that these are the main relays. The heavy current flows through it and do not touch it because they are taking current through this switch and the next switch, and you can see that a lot of thick conducting paths are being formed over here. So everything won't be visible at the top layer, but truth is that generally these will be the biggest switch present in AFE. Next thing is, I will a little bit quickly go through this part. That next thing we do is current sensing. In current sensing also we have two major things which we practically do, which is shunt resistor and Hall current sensor. Usually when we go for shunt current sensing, the purpose is to read through a current. So suppose a current is being flown and I want to read through it, I would look at current into resistance drop. But this is not enough to take care of everything. Actually, we take a very small resistance because we are flowing 100 ampere current here. With 100 ampere current, even a small resistance will give us some millivolts, tens of millivolts of data. But the other problem is when it is 100 ampere current, a small resistance like 1 milliohm gives 10-watt loss. And it will be a very big resistor. I mean, let me tell you, 10 watt is a very big number. So we go for a smaller resistance even. Like for example, I would like to go with 0.5 milliohm, even half of that. and there will be still 5 watt loss. Uh, Still the big resistor will come into picture, and that data we actually filter and amplify and send it to ADC. Why? Because it will be a small number. Like if you use 1 milliohm resistor, it will be 100 millivolts, which we are talking about. That is small voltage. And we need to read it to tell the data of current. Like half of the current is flowing 50 amps, the voltage will be 50 millivolt. And we want to actually sense it and go through it. Again, same situation will come up here, that through shunt resistor, if you want to have, you need to have a resistor which is not having lot of temperature dependency. That's why we use something like magning or Zerenin very low TCR resistor. We avoid a wire bound sort of resistor because it has parasitic inductance. And then next thing is we usually connect directly to the pad. So if you look at it, there are connections which are directly at the pad level. And then we filter this data and take that data for the current amplification. Now this is the real thing. So basically you have your current path. This resistance is sitting somewhere over here. And from that resistor, we have lot of filters connected. Generally, a common mode filter is connected to avoid all common mode noise. Then there is internal op amp connected like this, which avoids differential noise. So both noise we want to avoid. This configuration is a special filter which avoids common mode noise, and there will be internal setting op amp which will avoid the next noise, which is the differential noise, and then there is ADC. And something like zero point 0.1 microfarad capacitor and something like 10 kilo ohm resistor would be enough to filter the current scenario over here. One more important thing is that this shunt resistor can be kept at low end or it can be kept at high end. Generally, we call it high side current sensing or low side current sensing. Low side current sensing is preferable whenever we want to go with a simple system. But it has just one problem, that the load end is ground level and the battery pack level is actually not grounded. The negative terminal of the battery is at some voltage, like 100 amps current is flowing, it has 100 millivolt and it has zero. So basically load ground is shifted in this configuration. To avoid that shift and all, we actually connect a low side shunt resistor, um, but we connect another insulation resistor to chassis. There is another scheme in which we can put our current sensing at the high side, which is at high voltage side. And here the earth of load and the pack both are same, which is the good part. But the bigger problem is that when you sense this voltage, now this is high voltage side signal. High voltage side signal requires some additional circuitry, which I was telling you as filter. Before even that filter, we need to convert this data to low voltage because all microcontrollers are running at no voltage. So we have a trade-off to make here. Generally, a common scheme is low side current sensing, but people do high side current sensing. It has little bit more complexity, but it has some additional feature also, like there is a short circuit. So this resistor will experience all the short circuit current and you can detect a short circuit. But this resistor will not experience a lot of short circuit current because it's not sitting at the high voltage. So the short circuit will happen something like directly the current will go to the earth and come back to the pack negative. It may bypass the shunt resistor when it is sitting at low end. So that's why it is not preferred. Another method is to use a Hall effect current sensor. Usually a Hall effect current sensor is common when we are looking at high current ratings, but it has its own problem like EMI noise capturing and all those, because it is more like looking at magnetic field. But still, if you have something called as closed loop fluxicate ICs, they do really, really good. And this is what we use in high power EVs. Definitely LEM ICs most of the time are being used. But suppose you are developing for two-wheeler or three-wheeler, you would not like to go for 5,000 rupees sensor. So then you will have shunt sensing. which I was just discussing before this point, as the reliable one. And it is in good cost also. So this is a trade-off with the cost and performance. So very high end costly feature sort of application go for hall based. Low end application, low cost, you go for shunt sensing. Then there is another part which is more like data logging. So I told you that there is a central unit sitting, which is the microcontroller unit. It has some storage of the data within IC. So you need to connect some sort of ROM there. An IC would be sitting to store some data, a dedicated IC, not the microcontroller registers. And through that IC, which is the data log IC, we also want to send this signal for high-end processors to have a communication. So two basic things are there. Like one is data logging to keep the data record of everything which is happening. And the other thing is to communicate that data to high-end microcontrollers. That is also being done within let's say the IC. So these high-end processors which are sitting somewhere else, they would do the SOC and SOH sort of working. And it depends on various cell chemistry, various cell parameters to do that. But good part is this AFE usually do not depend on the cell chemistry. So that hardware card remains same. The higher end decisions which were being done in the high-end processor, which was responsible for the BM, their things will change based on the chemistry, based on the pack size. But based on the number of cells and parallel cells, if you design something like 12S12P sort of AFE card, and you have your own microcontroller and code setting there, you can easily use it to reconfigure something for 8 cells, 8PS, 8 sort of 8P, 8S sort of system, and that gives you customizability. That's why you should sort of make your own product. That's why you should make your own card. And that's why this discussion, which is implementation on the hardware side. So one last thing which I will tell you is that there are dedicated ICs for that. For example, TI makes some ICs called as BQ769-2X or 9XX series, which have dedicated IC feature like 3 to 5, 6 to 10, 9 to 15, and various voltage levels, because lesser number of cells means smaller voltage, higher number of series cells means higher voltage. And there are design guidelines in this also. Like you can look for their own design guidelines which are available on the website for TI. Whatever I have been telling you, those things they will implement in their own style, their own way, but the numbers won't change. Whatever I was telling you, like for the filters, for the samplers, for the sensing schemes, and the data equation, those all remain same, passive, active balancing. Just the thing is, to do that, whatever IC and the coding they need, they have put inside it. So this IC is having its own microcontroller, having its own basic embedded system running inside it, and various other aspects which are needed to run it. So basically, I would just go into 5 minutes more into this particular data and tell you that there is something called as design consideration document. So how do I know these many details? Definitely, I have made one BMS, but even before that, I have gone through such documents which are there, which tells you that how to design. So if you look at the details, they are giving every detail, like typical low side FET connection, how you need to do. If you want to do n channel sort of balancing, what you need to do. So all those things they are telling during this, we get to know what to keep our data. Like I was telling you earlier that 10 millisecond, 9.5 millisecond is a good sampling time. We are fine to go with it. So those ideas are coming up because I such IC details which tells me that okay, 12 millisecond is good enough. So definitely 10 to 12 millisecond. So if you go to design documents, you will find various details like PCB footprint, how it should be, how you connect them, like RC filters and everything, how these current transitions are being taken from these ICs. A little bit more complicacy will be there because the problem is these are single ICs trying to take care of many things. When you have our own let's say microcontrollers, our own switches sitting there, this complicacy is not that much. But I mean, it's their own way. That's how they want to do it. It's like this passive balancing, which I was telling you. So all the things they also do, they have their own dedicated IC and understanding around the IC. So you can go with this document. I mean, look into such documents. This is just one. I mean, there are many such ICs available within the BMS community to make an AFE card. And I would say that it's one of the very common topic, one of the very common hardware product which people make uh, to start with BMS. I mean, so that's why I chose this topic to discuss with, because this is one thing which is uh, very good at application, yet very fundamental, and it is very common, required at all battery level things. I mean, you take any battery example or battery bank example, you will find an AFE card sitting there. It may vary from the rating to rating which card it is, but card is there. So our own country scenario, we are actually not having any manufacturer yet for AFE cards. Um, Yet people are just going for assembly of some AFE card which they are buying from the market, battery pack which we are they buying from the market, just putting them together and selling, making some profit. But this can be tenfold profit if you make your own AFE card, your own hardware. So this is it from my side. Time constraint, I would like to stop over here, and I would request you to go through such other documents as well. It will actually give you some more idea into the field. Um, so I will stop over here. If you have some questions dedicated to this discussion, we can address them. Yeah.
Thank you so much, sir, for such informative session. To all the participants, if you have any question, you can either type in chat box or you can raise hand and ask question directly to sir.
So I don't see any question in the chat box. If something is there, please let me know. Maybe I'm not able to see in my screen. But by audio also, it's fine. I mean, anyone can ask. Fine to.
Someone is having any question, they can ask.
Okay, so I think we can suppose that um, either things are very clear or nothing is clear because doubts don't come in two scenarios only. So anyway, I mean, my email ID is mentioned over here. If any of you have any specific doubt, any research idea or anything you want to communicate with me, you can email at this address, and we can have a conversation regarding that. Today's session, I think that's it. That's it. So good day, all of you. Thanks all to attend and listen to the session. Thank you.
Thank you, sir. Thank you so much.